Hi everyone, today I'll be presenting my project on reinforcement learning beyond the perfect simulation, stress tests, and reinforcement learning algorithms against catastrophic failure. This project empirically measures and interprets how PPO and DQN degrade under probabilistic system failures across sensor, actuator dynamics, and catastrophic categories, simulating real-world hardware and environmental faults. The focus is on true complementary experiments and the lunar lander V2 environment to test generalization, the first experiment, and recovery, the second experiment. It's based on family-based failure for realism, so we can make sure that the stochasticity actually simulating some real-world failures and not just adding some Gaussian noise. 5 seeds, so we can make sure that we did not just get lucky by a lucky seed, and to reduce variance. Stable baseline 3 for implementation. So let's first start by understanding why robustness matters. The fundamental problem is reinforcement learning agents are typically trained in perfect idealized environments where we have perfect sensors, actions execute precisely, the environment stays constant, so we have like a success rate of 95%. But in reality, we might have sensors malfunction, motor slip, and drift conditions changes. We have a success rate that doesn't even get past 40%. This creates a dangerous deployment gap. Our project directly addresses this gap by systematically studying how modern reinforcement learning agents handle various types of system failures. Some example where this matters, for example, autonomous vehicles where we have unpredictable traffic and sensor noise, industrial robots where we have mechanical wear and friction variation, or maybe a spacecraft that might face thruster malfunctioning during critical maneuvers. And also for our experiments, the generalization and recovery. For the generalization, we want to investigate whether exposure to failures during training builds robustness, and critically, where there is an optimal level of failure exposure, because too little might have agents unprepared, and also too much might prevent them from learning effective policy at all. And for recovery, the second experiment, we want to understand the zero-shot robustness. For example, if we train an agent in perfect conditions and then deploy it in a failure-prone environment, how well this agent can perform. This represents the common real-world scenario where we can't anticipate every possible failure mode during development. Now let's discuss our choice for the environment, which is lunar lander. First, it's safety critical. Failure means crashing, which mirrors real aerospace and robotic applications, where mistakes have consequences. Second, it has rich dynamic involving continuous control of position, velocity, and the angle. This complexity actually allows us to introduce realistic, diverse failure modes. Third, it has multiple subsystems. The sensor that provides the state information, the actuators that control the thrusters, and dynamics govern physics, each of which can fail independently, just like real systems. Fourth, there is a clear success criterion, landing safely between the two yellow flags with minimal fuel consumption. Landing there might give us like a reward above 200, because landing gives a reward of plus 200, crashing minus 200, and each step without crashing gives a plus reward, which gives us an objective measure of performance. Finally, the episode structure allows us to study failure time and effects. Doesn't matter if we fail early in the episode or later in the episode. Our stochasticity design is carefully engineered to mirror real-world failure patterns and not just adding some random noise to the observation, for example. We implemented episode level randomization, which is crucial. Um, at the start of each episode, we decide whether a failure might occur based on a failure probability parameter. If a failure is selected, then all its characteristics are sampled once and processed through the episode. This reflects reality because a sensor doesn't randomly fix itself mid-flight, and the actuator degradation doesn't fluctuate randomly. Then we select from four failure families, each representing a distinct failure mode with encounter in real systems. The severity is sampled from 0.3 to 1, representing mild to severe degradation. Also, we introduced a failure onset time failures, a failure that don't occur like at step 0, but rather between steps 20 to 200, which models the realistic scenario where system operates normally initially, then degrade during the operation. This timing aspect is key for studying whether agents can detect and adapt to failure during execution. Now let's detail more about our four failures families. First, we have the sensor failures family that represents perception degradation. We implement grayscope scaling errors. Imagine, for example, a faulty providing incorrect angular velocity readings. We added also velocity measurement bias like a Python tube with calibration drift. We simulate sensor dropout where certain state's dimensions freezes. That, that actually mimics the communication loss problem or the sensor hang. We also implement accumulating alimenters drifts that represent gradual sensor degradation over the time. Second, we have actuator failures that affect control authority. These include thrust degradation, for example, when an engine loses power output or an asymmetric thruster response, causing uncontrolled rotation and control delays, where commands are not executed immediately. We even model stochastic actuator lag based on the severity levels we discussed earlier. Dynamic failures alter the environment's physics. Mass loss represents fuel depletion or structural damage. The gravity variation could also represent different planetary bodies or atmospheric effects. Persistent one forces the agent to compensate for external disturbance. The catastrophic failures represent complete subsystem loss, total engine cutoffs, or landing gear failure that turns any landing into a crash. These are the worst case scenarios. For each failure type is parameterized by severity, making effects proportional to how bad the failure is. And to ensure the validation of the stochasticity implementation, a key challenge was ensuring failure onset timing worked correctly. We sample failure step parameter once per episode during reset. All failures effects are conditioned on the variable current step that must be superior or equal to failure step variable, which ensures failures don't activate prematurely. Now for algorithm selection, we selected DQN as our value-based representative. In the implementation, we used a learning rate of 10 to the power of minus 3, which is relatively high, but DQN's experience replay and target network provide stability. A batch size of 64 that balances gradient, noise, and computational efficiency. We start the learning after the 10K steps to ensure the buffer has diverse experiences to learn from. Uh, the exploration schedule is crucial. We decay the epsilon from 1 to 0.05 over 20% of training. That gives the agent substantial time to explore under failures before exploitation. PPO, Proximal Policy Optimization, selected as our policy-based approach. The implementation differs from DQN. For example, a learning rate of 3 multiplied by 10 to the power of -4, which is a standard PPO's learning rate, which is proven robust across many tasks, and training time steps of 1 million, because we actually want to ensure that both algorithms reaches convergence, so that it can be fair enough to compare both of them. And actually, we did this across 16 parallel environments, so effective environment steps are similar to DQN. N steps, the number of steps, 2048 means we collect 2048 steps from each of the 16 environments before each policy update. The clip range of 0.2 that prevents destructively large policy updates, which is especially important when failures cause sudden reward change. We set the entropy coefficient to 0 because lunar lander doesn't need additional exploration bonus. The task itself provides sufficient learning signals. So about the 16 parallel environments, that might sound like it's not fair to use it on PPO and not on DQN. Actually, this is not just for speed because PPO took too much time training. It's architecturally motivated. PPO is on policy algorithm, meaning it only learns from data collected by the current policy. The data becomes stale immediately after a policy update. The parallel environments solves this by providing diverse experiences simultaneously, which is crucial when failures are stochastic. So each of the 16 environments can experience different failure types, severities, and timing in the same rollout phase, giving PPO a richer learning signal about how to handle various failure scenarios. As for DQN, we avoided vectorization because the experience replay already provides the correlation of information, and single environment training gives us finer control over the failure distribution. DQN is off policy, means we can reuse the old data, so we don't need the truth path vectorization that the vectorization provides. This difference is not just implementation details, it reflects the fundamental algorithmic differences between the on and off policy methods. Now let's talk a little bit more about our experiments. The first experiment, generalization, it tests failure exposure during training if it creates policies that generalize to varying real-world states. In other way, it helps answer the question of, does training with failure helps to learn a more robust policy? This is our comprehensive cross-evaluation study, designed to understand the relationship between training conditions and generalization. For training, we train agents at 6 failure probabilities levels from 0% to 25%. Each represents increase in exposure to failures during training. Then we test each agent at all 6 failures levels, creating a 6 by 6 matrix of train test combination. And to note, we use 5 different random seeds for each training configuration. That gives us 30 agents per algorithms. Then we average them for each stochasticity level, so we can make sure that we did not just get lucky by one seed. As for the second experiment that measures the zero-shot recovery, it helps answer the question of, can the agent recover from a mid-air breakdown? This experiment focuses specifically on the zero-shot scenario, the most common real-world case where we train in ideal conditions but deploy in imperfect ones. For training, we train 5 agents per algorithm exclusively at 0% failure probability or, well, stochasticity level. Um, Perfect conditions with no failures at all. Then we evaluate agents across all 6 test failures probabilities. The experiment is practically important because it represents reality for most reinforcement learning deployments. We typically develop and train in simulators or controlled environments where we can ensure repeatability. Then we deploy to the real world where things might go wrong. For this experiment, we also record the last 10 episodes with failures as gifts to qualitatively analyze agent behavior when facing unexpected failures. We will see these gifts at the end of the presentation. For evaluation metrics, our metric selection is deliberate and multifaceted. We need multiple perspectives to understand robustness comprehensively. For For experiment 1, mean return is our primary performance indicator. In lunar lander, rewards accumulate based on descent rate, fuel efficiency, landing precision, and landing outcome. A reward above 200 indicates successful landing. Return gives us a continuous measure of how well agents perform, capturing both task completion and efficiency. The success rate is our binary outcome measure, the proportion of episodes achieving reward above 200, which is crucial because in safety critical applications, we care about reliability. An agent that lands successfully 90% of the time might be acceptable for more applications, but not for crewed missions. Crash rate. This measures the catastrophic failures. Episodes with the return below 100 indicates high speed impacts or out of bound crashes. This is our safety metrics. In real aerospace applications, a crash is unacceptable, regardless of how well the agent performed in other episodes. The episode length, which tells us about mission duration and agent efficiency. Longer episodes might indicate hesitation or inefficient policies. Very short episodes typically indicates immediate crashes. The nominal episode length is around 300, 600 steps for successful landing. As for experiment 2, we track failure specific metrics that provides deeper insights into the agent behavior and their failures. Time to failure. This measures when during the episode the failure occurred. This is our failure step value. Sample between steps 20 to and 200. At episode start, this metrics matters because failure timing affects difficulty. For example, a failure at step 50 when the lander is high altitude is different from a failure at steps 180 during the final approach. By tracking this, we can analyze whether agents are more vulnerable at specific mission phases. The pre-fault return accumulates reward before failure onset. This tells us if agent can perform nominally when everything works correctly. If pre-fault return is consistently high, the agent has learned a good base policy. And if it's low, even before failures, then the training itself was problematic. The post-failure return. This is critical because it measures the performance after failure activation. A dramatic drop in post-fault return indicates that the agent can't adapt to changed conditions. A modest drop suggests some resilience. In some rare cases, post-fault return might be higher if the agent accidentally benefits from a failure, uh, but this is uncommon and logically can't happen. The ratio of pre-fault to post-fault return quantifies resilience. Uh, it can be a ratio near 1, means the agent maintains performance despite failure. A ratio near 0 or can be negative means complete performance collapse. So now let's look at some results, starting with the results of DQN on experiment 1, the generalization experiments. So this heat maps shows the DQN success rates, the crash rate, and the mean return, also the curves of robustness. So the most striking results is that the DQN struggles severely with failures almost across all the conditions. Even the agents trained at 0% and tested at 0% only achieves around 51% of the success rate, which is concerning, and it might suggest that the DQN might be fundamentally challenged by this task, at least with our training configurations, of course. So if we take a look at the diagonal, which represents matched training and testing levels, we don't see strong performance anywhere. There is no failure probability level where the DQ1 learns reliably. When we look at the generalization, the off-diagonal entries, we see essentially like uniform low performance. Agents trained at any level perform similarly poor across all the test levels. The performance is very low. That generalization patterns are masked by floor effects. But in an interesting way, we can see that the Asian trained at 0% failure actually performs slightly better at the test time on all the levels compared to Asians whom are trained on some level of failure probability. This actually might be because the DQ1 trained with some failures, it prevented from learning any coherent policy at all. While for 0% training, at least it allows it to learn a policy, even though it might not be robust, but at least it learns some policy. For the crash rate, it's actually a similar story, very high across almost all conditions, indicating the agents frequently have catastrophic failures. The highest, the lowest, pardon, the lowest crash rate is interestingly of 5%, trained on 5%, and tested on 0%. But it tells the overall the agents that are trained on the 0% outperform the other where we injected some stochasticity. The mean return is also very low. The highest one doesn't surpass 200, and for the robustness curves, the most robust one is the agents that are trained on 0%. Now let's move to the results of experiments for DQN also. So the agents are all trained on 0% failure probability. The best case scenario is when it's tested on 0% failure probability also. This is our best case baseline, and it's barely above random chances. It doesn't surpass 51%. A test failure probability increases from 0 to 25% success rate actually fluctuates but remains in the range of 45% to 50% range. The lack of monotonic decline is puzzling, with expect steady degradation, which suggests that DQN's performance is dominated by noise rather than systematic behavior patterns. For the mean time to failure, the figure shows that failure typically occur around 460 to 590 steps into the episodes, which is mid to late in the episode length. This means the agent often survives the initial phase but fails during critical descent or even landing. Both figures of mean pre-fault return and mean post-fault return uh, would be enlightening, but with such low baseline success rate, both of them returns are likely negative or near zero here, or near zero, which indicates poor performance through the episode. The critical failure threshold appears to be around 5%. Even minimal failure probability drops success below 50%, which indicates that the DQN has essentially zero robustness to failure in this task with our training configuration, of course. Now let's move to the results of experiments for DQN also. So the agents are all trained on 0% failure probability. The best case scenario is when it's tested on 0% failure probability also. This is our best case baseline, and it's barely above random chances. It doesn't surpass 51%. A test failure probability increases from 0 to 25% success rate actually fluctuates but remains in the range of 45% to 50% range. The lack of monotonic decline is puzzling, with expect steady degradation, which suggests that DQN's performance is dominated by noise rather than systematic behavior patterns. For the mean time to failure, the figure shows that failure typically occur around 460 to 590 steps into the episodes, which is mid to late in the episode length. This means the agent often survives the initial phase but fails during critical descent or even landing. Both figures of mean pre-fault return and mean post-fault return would be enlightening, but with such low baseline success rate, both of them returns are likely negative or near zero here, or near zero, which indicates poor performance through the episode. The critical failure threshold appears to be around 5%. Even minimal failure probability drops success below 50%, which indicates that the DQN has essentially zero robustness to failure in this task with our training configuration, of course. Here we can see the struggle of an example of the seed 7029 on two different stochasticity levels. Now let's move to the results of PPO on the first experiments, of course. We can clearly see that the PPO's result paints a dramatically different picture. This is where we see the power of policy-based methods. We can see on the heat map of success rate that the agents trained at the 0% failure achieves approximately 89% success rate when tested at 0%, which is a strong baseline performance. And as test failure probability increases, we see graceful degradation from like 87% to drop into 75% but at 25% test failure probability. This is exactly the pattern we want to see: monotonic, gradual decline rather than catastrophic failure as we saw earlier with the DQN. Here, the agent maintains above threshold performance up to 20% failures, only dropping on the 25% failure test probability, because uh, that level of failure is honestly a little bit brutal. However, training at very high failure probabilities for 20% or 25% degrades performance even at test time with the same failure rate, which indicates that too much disruption during the training. The agent can't learn a coherent policy when failures are too frequent. And if we take a look at the agents trained at 5% failures, produces agents that perform well across most test conditions, sometimes even better than 0% trained agents at moderate failure levels, which suggests some failure exposure helps generalization, which is exactly what was our hypothesis when we talked about the experiment 1 earlier. The generalization gap between diagonal and off-diagonal is small, only about 0.3 percentage points, which indicates that the PPO agents generalize very well to slightly different failure rates rather than they trained with. So the optimal strategy appears to be training at 0% to 5% failure for deployment across a range of failures. If we take a look at the crash rate, we can clearly see that it's very good, and the results are slightly good, more than the DQ1. The same thing for the mean return. The highest value is 200, approximately 250, which surpasses the threshold of 200's mean return. And for the robustness curves, we can see that the most robust one is alternating actually between the ones trained at 0% and 5%, but we can see the 5% the majority of the time outperforms the one of 0%. Moving to the results of experiments 2, the zero-shot robustness. Actually, it's quite impressive and provide actionable insights. Starting at the 89% success in perfect conditions, trained at 0, of course, and tested at 0%. The PPO maintains above 85% success up to the 10% test failure. Even at 25% failure, the most extreme condition, the success rate was 75, approximately 75%, which represents only 15% point drop across the entire failure range. Critically, there is no identifiable critical failure threshold where the performance collapse. The degradation is linear and gradual, which is ideal for real-world deployment because we can predict the performance at untested failure rates through interpolation. The crash rate remains remarkably low across all failures condition, staying below 10%, and even at 25% failures. This indicates that PPO agents fail gracefully when they fail, often through timeout or suboptimal landing rather than catastrophic crashes. For time to failure analysis, This shows failures typically occur around 200, 282 and 340 approximately steps, which is mid-episode. And the fact that episode length does not dramatically decreases with failure probability suggests that the agents don't immediately crash upon a failure, but they attempt to compensate. For both the plots of mean pre-fault return and the post-fault return analysis, they show strong pre-fault performance, and for post-fault return, it's modest. Indication agents actually execute well initially and maintains partial capability after the failures occur. The zero-shot robustness for PPO results are very remarkable. The agents actually trained without any failure experience still maintains functionality across a wide range of failure scenarios. Now the recorded episodes of the 6174 are two different tested, not trained, failure rates. Now let's move to the algorithm comparison. It was clear that the PPO outperformed DQN, but let's analyze it more. 0% test failures, PPO outperforms DQN by like 38 percentage point. That indicates the PPO simply learned the task better in both cases, regardless of failures. As failure increases up to 25%, the PPO maintains approximately 75, let's say, percent success, while DQN drops down to 45%. Approximately 30% percentage point gap. So PPO's advantage actually decreases slightly at high failure rates, but it remains substantial. So why does PPO so dramatically outperform DQN? I believe there is several factor contributes. For example, we use it parallel environments training, which expose it to diverse experiences simultaneously, even at 0% failure training. The 16 environments provide variety in initial conditions, teaching PPO to handle variability. Second, PPO actually directly optimizes a stochastic policy. This might inherently provides robustness. The policy has learned to maintain a distribution over actions rather than committing to some deterministic choices. When failures corrupt state information, this stochasticity actually helps. And for third, PPOs as own policy learning means it never trains on outdated experiences from different policy. Meanwhile, DQN's experience reply, while stabilizing means it trains on data from older, potentially ever different policies and their failures. This might cause some issues. PPO's trust region prevents catastrophic forgetting. The clipped objective ensures smooth updates, preventing sudden performance collapse if a batch happens to contain many failure cases. As for the limitations, first we studied a single environment, lunar lander. While it's rich and complex, generalization to other tasks is uncertain, so future work should replicate this analysis on other continuous control tasks like bipedal walking or robotic manipulation. As for our training budget, 700K for DQN might not be optimal. Perhaps it would perform better with more training. Through our learning curve suggested conversions, hyperparameters tuning focuses on robustness rather than nominal performance could maybe improve the results. Also, we don't explore ensemble methods or uncertainty-aware policies because agents that estimate their own confidence could maybe behave more conservatively under uncertainty. That might actually potentially improve the robustness. And in conclusion, we've presented a comprehensive study of deep reinforcement learning robustness under realistic stochastic failures, different families. Our results clearly demonstrates the PPO's superiority over DQN for robust control, identify optimal training strategies, and characterize graceful versus catastrophic degradation patterns. Beyond the specific findings, we've contributed methodology, a reusable experiment framework for robustness evaluation, comprehensive metrics beyond simple success rate, and direct algorithm comparison under controlled conditions. And thank you for your attention. And if you'd like to ask any question, feel free.